To better understand torque, we're going to work through three examples. We're going to balance masses on either side of a fulcrum. We are also going to talk about the lever and then a screwdriver handle. Here's a balance with two masses attached to it. Here's the balance. All right, we have this horizontal piece, and then it's on a vertical piece, and we have some kind of pin or fulcrum here. Block A has a mass of 0.67 kilograms, and its distance from the pivot point, R sub A, is 0.23 meters. We want to hang a block B here, mass of 1.2 kilograms. Where should it be located so that the balance beam is perfectly horizontal and is not moving? Is this a translational motion problem or a rotational motion problem? And this arrow, double-headed arrow here, indicates where on this line will I put the mass. And that distance, wherever I put it, between the support point and the center here would be called R sub B. First, an artistic hint. This is a seesaw. This is something kids used to play with in the old days. The two boys on the left represent mass A, and we're going to assume they're a little lighter than these two boys. These guys are mass B. We're going to assume they're heavier, and this distance here is smaller than the distance between this pivot point and where these boys are. One question is, why aren't these guys colored in? But that's more for artists to think about. And a side note, there are many connections between physics and art and music. That would be an excellent project to research. But let's get back to the physics on the next page. Whether you have a translational or a rotational dynamics problem, you start them the same way. You start with a free body diagram. And in this case, we're going to look at this point here, point A, and we're going to construct a free body diagram for point A, and also we're going to have one for point B. Now we know that there are certainly tension forces pulling it each way, and we're not going to worry about that direction because we know that this beam is not going to move left or right. It's not going to move up or down. But what will happen, for example, if I had a mass here and no mass here, it would rotate this way. It would rotate counterclockwise. So to answer the question from a couple pages ago, we have a rotational problem. I have a mass pulling down at point A, so that force is ma times g. When I calculate the torque, that will be the distance from the middle, which in this case is Ra, times the force, times sine theta. Theta is 90 degrees. We do the same thing at point B, and in that case it's mass B times g, and the torque is negative in this case. Why? A is trying to rotate about this pivot point in a counterclockwise direction. So we give that a positive sign, or leave the sign out, same thing. B is trying to move it in a clockwise direction. So that is a negative torque. And right here, you can see the negative. This is a rotational motion problem, so in order to have the beam not rotate, the sum of the torques applied to it must equal 0. No forces, it's not going to move from rest. So we will sum our torques up, we'll have them equal 0. Here's the torque due to mass A, it's a positive. Here's the torque due to mass B, that's negative. We cancel out the sine thetas. Actually, since they're both 90, they would equal 1 anyway, but no matter what angle, they cancel. We substitute in for the force, which was mg, do a little more rearranging, and then we have the distance of object B is mass A over mass B times Ra, and we come up with that distance Rb is equal to 0.13 meters. Showing the value of both art and, frankly, playing in the playground during elementary school, kids already know this. If you're on a seesaw or a balance, and you have to balance several larger students on the other side, so let's draw over here. So if here's our fulcrum, and you want to balance out you have some big kids here. I'll just represent them by a big block. And then I'll represent you, because you're just one person, as a little block. You know that you want to be further away from the fulcrum than the big kids. So here's the seesaw. Most of the time they're the same length. So you want the bigger kids closer to the fulcrum. You can then lift them up and stay balanced.